In today's video, we'll learn about the intensity of sound waves. The average intensity of a wave on a given surface is defined as the rate at which energy flows through the surface, which is measured by our change in energy divided by our change in time, divided by the surface area. So we see that our intensity is equal to 1 divided by our surface area multiplied by our change in energy divided by our change in time. And we express intensity in the SI units of watt per meter squared. And since our rate of energy transfer is also equivalent to power, our intensity can be defined as the power of the sound passing through the surface, which is measured in watts, divided by the surface area. Intensity can be measured in decibels, so that the relative intensity of a sound is defined by our decibel level, which is given to us by the equation that beta is equivalent to 10 multiplied by the log of our intensity divided by our reference intensity, which is the sound intensity that is at the threshold of hearing and has a constant of 1.0 times 10 to the negative 12th power watts per meter squared. We represent decibels by the symbol beta, and our decibels are measured and expressed in dB. If we look at our chart to the right, we see we have increasing decibel levels corresponding to loudness. We see that as the decibels increase, our loudness increases. And at 125 decibels, we reach the threshold of pain. So any sound intensity equivalent to or over 125 decibels can result in painful hearing. Looking at our example given, it states that an outside loudspeaker emits sound waves with a power output of 100 watts. In part A, we're asked to find the intensity of the sound if it is measured from the source at a distance of 10 meters. So we start by summarizing the information we're given. We're given that the power output of the speaker is 100 watts, and we're asked to find the sound intensity at a distance of 10 meters. So we know that intensity is measured by our power divided by our area. We're given our power, however, we're not given our area. But since we know that sound waves radiate equally in each direction, we can imagine that our sound waves would take on the shape of a sphere. And so we know that the surface area of a sphere is 4 pi multiplied by a radius squared. So given that our displacement from the source is 10 meters, our radius will be 10 meters. So if we plug in what we know, we can solve for our intensity of the sound. So our power is given to us as 100 watts divided by 4 pi multiplied by our radius, which is 10 meters squared. And so when we calculate this out, we see that our intensity of the sound heard at 10 meters away from the source will be equivalent to 7.96 times 10 to the negative second power watts per meter squared. In part B, we're asked to find the intensity level in decibels at the same distance. So in part B, we know that our decibel level is measured by the equation that beta is equal to 10 multiplied by the log of our intensity divided by our reference intensity. Given that we solved for our intensity in part A and our reference intensity is a constant, we can solve for our intensity level in decibels. So we see that 10 multiplied by the log of 7.96 times 10 to the negative second power watts per meter squared divided by our reference intensity, which is a constant value of 1.0 times 10 to the negative 12 watts per meter squared. So we can solve our equation to solve for beta. And we see that beta will be equal to 109 decibels. Finally, in part C, we're asked, at what distance would you experience the sound at the threshold of pain, which is said to be experienced at 120 decibels? So the only equation where we have some form of distance is our equation that our intensity is equal to our power divided by 4 pi multiplied by our radius squared. And so we can rearrange this equation to solve for r, which will be our radius or our distance where we would experience the threshold of pain. So if we were to rearrange our equation to solve for our radius, we would end up with the equation that the square root of our power divided by 4 pi multiplied by our intensity would give us our radius where we would experience the threshold of pain. However, in our equation, we have the intensity level of sound, and in part C, we're given the decibel level of sound. So first, we will have to convert our decibel level into an intensity level, which we can do with the equation that beta, which is our decibel level, is equal to 10 multiplied by the log of our intensity divided by our reference intensity. And so since we're trying to solve for intensity, we'll have to rearrange the equation. So we know that our decibel level is given to us as 120 decibels equal to 10 multiplied by the log of our intensity, which is unknown, divided by our reference intensity, which has a value of 1.0 times 10 to the negative 12 watts per meter. So we can start by dividing each side by 10, which will give us that 12 is equal to our log of our intensity divided by our reference intensity, which can be written as 10 to the negative 12th power. We can then get rid of our log, and when we do so, we'll end up with the equation that 10 to the power of 12 is equal to our intensity divided by our reference intensity. And then by multiplying each side by 10 to the negative 12th, we'll see that our intensity is equal to 1.0 watts per meter squared. So now that we know our intensity at the threshold of pain, we can plug it into our equation to solve for our radius. And if we do so, we'll given the equation that the square root of our power of 100 watts divided by 4 pi multiplied by our intensity of 1.0 watts per meter squared will give us a radius that is equivalent to 2.82 meters. So in order to hear the threshold of pain, we would need to be 2.82 meters away from the source of the sound.